All right, in this chapter, we're going to dive into the really fascinating world of distributed software engineering. We'll be looking at how today's applications are built, not on just one computer, but across a whole network of computers that all work together. This is such a core concept in computing today. I mean, think about it. Whether you're streaming a movie, working on a shared document, or just doing a quick web search, you are using a distributed system. The real magic, though, is that it's all designed to feel like you're just interacting with one single, smooth system.
Okay, so here's what we've got on the agenda. We'll kick things off by defining what distributed systems actually are. Then we'll get into the big design challenges they present. After that, we'll break down client-server computing, look at some common architectural patterns, and wrap it all up with the rise of SaaS, or software as a service. Let's get started.
All right, section 1. So first things first, what are distributed systems really?
So this definition from Tannenbaum and Van Steen is pretty much perfect. It says, a distributed system is a collection of independent computers that appears to the user as a single coherent system. The key phrase there is appears to the user as a single system. It's all about creating an illusion, a kind of abstraction. You're taking a bunch of separate, networked computers and making them act like one. A search engine is a fantastic example, right? You type something in and it feels like you're talking to this one giant, all-knowing brain. But what's really happening is your query is being shot out to maybe thousands of different servers, all working together to get you an answer. Hiding all that background chaos, that's the mark of a great distributed system.
So, you might be wondering, why bother with all this complexity? Well, the payoffs are huge. First up, you get resource sharing. The classic example is one printer serving a whole office over the network. Simple but powerful. Then there's openness, which is all about using standard ways for things to talk to each other so you can mix and match components from different creators. Concurrency is another big win. You can have multiple things happening at the same time on different machines, which just speeds everything up. Scalability? This is probably the biggest reason we do this today. Instead of building one massive, super expensive computer, you can just add more cheaper computers to the system as you get more users. And finally, fault tolerance. This means if one machine in your network goes down, the whole system doesn't crash. It can keep on running, which is obviously critical.
Okay, so how do all these independent computers actually talk to one another? Let's use a simple restaurant analogy to break it down. The first way is what we call procedural interaction. Just imagine you're having a back-and-forth chat with your waiter. You say, "I'll have the soup." And then you have to wait for them to write it down and say, "Okay," before you can order your main course. It's step by step. This is what we call a synchronous interaction. One thing has to finish completely before the next one can start. In the computer world, we see this all the time with something called a remote procedure call, or RPC. It's basically one computer telling another, "Hey, run this piece of code for me," and then it just waits until it gets the result back.
Now, the other model is message-based interaction. Sticking with our restaurant, imagine the waiter takes everyone's order, writes it all down on one ticket, and then just hands that ticket to the kitchen. That ticket is one complete, self-contained message. The kitchen has everything it needs, and the waiter? They don't have to stand there and wait. They can go off and take another order or refill drinks. This is asynchronous. They send the message and move on.
So, as you can probably guess, these two different styles lead to very different kinds of systems. The procedural way, that RPC style, is what we call tightly coupled. This means both the sender and the receiver have to be online and available at the exact same time. The waiter and the chef have to be talking directly. If the chef steps out for a minute, the whole conversation stops. The message-based style, on the other hand, is loosely coupled. The sender doesn't need to know if the receiver is available right now. The waiter just needs to know where to put the ticket. The message can just sit in a queue, waiting for the chef to come back and pick it up. This makes the whole system a lot more robust and able to handle delays or temporary outages.
Okay, so here's a big question. How do all these different parts, which might be written in totally different programming languages, running on different computers, actually communicate? The magic ingredient here is something called middleware. You can think of it as the glue that holds everything together. It's this software layer that sits in the middle and acts like a universal translator or a traffic cop for the system. It handles all the messy, low-level stuff like making sure messages get delivered, translating data formats, handling security, all that plumbing. This is huge because it means application developers don't have to worry about it. They can just focus on building the features that users actually care about. All right, on to our next section. Now, these systems are super powerful, but that power definitely comes with its own set of really tough design challenges that engineers have to wrestle with. When you're building one of these systems, you're constantly dealing with a bunch of core design issues. Take transparency. How much of the system's inner workings do you hide from the user? Do you try to make it seem like one machine or not? Then there's openness. Do you stick to standard protocols that everyone can use, or do you invent your own that might be faster but locks you in? Scalability is always a huge one. How do you build this thing so it can go from a handful of users to millions without falling over? Security gets way harder when your system is spread out all over the place. Quality of service is all about making sure the system is reliable and performs well. And then there's the big one, failure management. Things are going to break. It's inevitable. So how do you spot failures, stop them from spreading, and recover without the user even noticing?
And on that note, this famous quote from Leslie Lamport just absolutely nails the problem of failure. You know that you have a distributed system when the crash of a system that you've never heard of stops you getting any work done. It's funny because it's so true. In these massive interconnected systems, some random obscure part can fail and suddenly the whole thing grinds to a halt. It's like a domino effect. And engineering systems to be resilient to that kind of chaos is, without a doubt, one of the hardest jobs in software.
Okay, let's move on and talk about the most common way these systems are organized. I'm sure you've heard of this one before, client-server computing.
So to really get the client-server model, it helps to think of any application as being built in logical layers. At the top, you have the presentation layer. That's the user interface, what you actually see and click on. Next is data handling, which does things like checking that you entered a valid email address. Then you've got the application processing layer. This is the real brain of the operation, where all the core logic happens. And at the bottom, the database layer, which is all about storing and retrieving information. Now, the entire game with client-server architecture is figuring out how to split these 4 layers between the client machine and the server machine.
And how you split those layers leads to 2 classic approaches. On the one hand, you have the thin client model. Here, the client's job is super simple. It just shows you stuff. Your web browser's the perfect example of a thin client. All the heavy lifting, the application logic, the database stuff, that all happens on the server. The big plus, it's easy to manage. You just update the server and everyone gets the new version. The downside, the server can get totally overloaded. On the other hand, you have the fat client model. In this case, the client machine does a lot more work, handling both the presentation and the application logic. Think of a big desktop program, like a video game. This takes a huge load off the server, but now you have a new problem. You have to install and maintain that complex software on every single person's computer.
Well, because both of those 2-tier models had their limitations, things evolved into what we call multi-tier architectures. An online banking system is a perfect real-world example. You've got 3 tiers here. Tier 1 is your web browser, the client. Tier 2 is a web server, which handles the application logic. And Tier 3 is a totally separate database server. The reason this is so great is for scalability. If your website suddenly gets super popular and the web server is struggling, you can just add more web servers to the mix. You don't have to touch the database server at all. It makes scaling up way, way easier. Okay, so let's take this a step further and look at some formal distributed architectural patterns. You can think of these just like blueprints in construction. They're proven, reusable solutions to common problems. A classic pattern is the master-slave architecture, though it's worth noting that today people often use more modern terms like controller worker or primary replica. The idea is really simple. You have one master process. That's the boss. It's in charge of coordination and tells all the slave or worker processes what to do. The workers then go off and do very specific jobs. Like in this traffic control system, the master is the central brain, and the workers are the little processes controlling individual traffic lights or reading data from sensors. It gives you a very clear, centralized command structure, which is great for systems where timing and control are critical. Now, for a more flexible, modern approach, we have the distributed component architecture. Instead of rigid layers, you think of your system as a collection of independent components, almost like Lego blocks. Each block provides a specific service. So in this data mining example, you'd have one component for getting data, another for integrating it, and a third for creating visualizations. The real beauty of this is that the components are interchangeable. If you want a better visualization tool, you can just swap out that one component without having to rebuild the entire system. It makes everything much more flexible and easier to update.
And then you have peer-to-peer, or P2P, which completely flips the client-server model on its head. In a P2P network, there's no special server. Every single computer, or peer, is an equal. It can act as a client asking for things and as a server providing things. Now, there are a couple of flavors of this. On the left, you see a purely decentralized network where peers just find each other and talk directly. On the right, you have a semi-centralized version, which is actually more common. There's a central server, but its only job is to introduce peers to each other. Once they've been introduced, they go back to talking directly, peer-to-peer.
Okay,
last section. So how does all this stuff, client server, these different patterns, how does it all come together in the real world today? Well, it all leads to something you definitely use every day, software as a service, or SaaS.
So what exactly is SaaS? It really boils down to three main things. First, the software lives on a server somewhere, not on your computer. You just access it through your web browser. Second, the company that makes the software owns and manages everything. The servers, the updates, all of it. You don't have to worry about any of that. And third, you usually pay for it with a subscription instead of buying it outright. Think about services like Office 365 or Google Docs. Those are perfect examples of SaaS. But this whole model creates a huge engineering puzzle. If you're a SaaS company, you want to run just one copy of your software, right? But you need that one application to serve thousands of different customers. We call them tenants. So the big question is, how on earth do you do that efficiently while making absolutely sure that one customer can never, ever see another customer's private data?
And the answer to that puzzle is a really clever concept called multi-tenancy. The main idea is that all the customers, or tenants, share the same database. This is way cheaper and more efficient than having a separate database for every single customer. So how is it secure? Well, that's where data partitioning comes in. If you look at this table, you'll see every row of data has a tenant ID. That ID is the secret sauce. The software is built so that whenever it fetches data, it always includes a check for that tenant ID. So even though data from XYZ Corp and JBowie might be physically stored right next to each other, the software builds an invisible wall between them. It's logically impossible for one tenant to see another's data.
So to wrap things up, what are the big takeaways? First, distributed systems are all about getting incredible scalability and fault tolerance, but you have to accept that they're just more complex to build. Second, we use these fundamental blueprints, these architectural patterns like client-server and peer-to-peer, to manage that complexity. And finally, all of these ideas are what make modern SaaS possible, allowing us to use powerful software right from our browsers. And that leaves us with a final thought to chew on. As our internet connections get faster and more reliable, are we headed for a future where all software is a service? Will the whole idea of installing a program on your computer eventually seem totally old-fashioned?